The next two lessons actually go into topics that you should recall either from grade 11 math or from work we've kind of already discussed in this class. We're going to start talking about money, investing money. That's probably a topic of conversation that happens lots. We hope that we don't get charged interest when we borrow money from our parents, but eventually we pay interest on loans and credit cards and our house purchases, and it's good to understand how that works. And it's related to exponential equations, which is why we're doing it again. Simple interest, you'll remember what that formula is. Interest, simple interest equals principal times rate times time. Uh, it's a nice calculation, and the formula is down here as well. Principal is the amount of money you borrow. Rate is the interest rate that you're getting converted into a decimal, and time is the number of years that you watch it grow. We're going to go to talking about compound interest, and compound interest is the type of interest I hope that I get in my investments. Compound interest pays my interest on a regular basis so that my money grows. If you're already investing in RRSPs or RESPs, you might be investing in that. The advantage is to start young because you get paid interest on your interest, which accumulates faster over time, and you're looking for that growth factor. So Canada savings bonds used to be something that our family purchased. Regular savings bonds might be paid with simple interest. Compound savings bonds, the interest rate might be a little bit lower, but you ended up getting more money at the end. If the interest rate is the same, the advantage is for compound interest. We're going to take a look at another chart. So let's turn the page one more time. I'm all the way to page 244, where we're just going to highlight the compound interest formula again. The compound interest formula has an exponent and a power that we have to deal with. The I is the interest rate per compounding period, and we're going to take a look at a chart where we take the annual interest rate, the annual I, and divide by the number of periods in a year. We'll take a look at how that runs. And N is the number of compounding periods you get in a year. We're going to fool around with that as well, the number of compounding periods that you get for the time of the investment. So sliding down a little bit, annual rate of interest means what for the number of compounding periods. We're going for 5 years. So if I'm getting paid interest annually, I'm getting one compounding period per year, and I'm running that for 5 years. The interest rate per compounding period is 6 divided by 1 converted into a percentage. If I go semi-annually, I'm going to get 2 compounding periods, which gives me in 5 years 10 compounding periods. My interest rates get split. So I get half my interest at the half of the year. Quarterly means I'm going to get interest 4 times in the year. So 4 times 5 is 20 compounding periods. My interest gets divided into 4. So 6 divided by 4. Monthly, that's 12 compounding periods per year. 12 times 5 is 60 compounding periods. My interest rate gets cut by 12. So my interest rate doesn't look so good by the time I get to compounding daily. 6 divided by 12. And it gets even worse if you add daily interest. When I was in high school, I had a daily savings interest account, which means I got paid interest 365 times in a year. And if I let that go for 5 years, 365 on a calculator that might actually work. This one has finally blown up. 365 times 5. 1,825 compounding periods. My interest rate gets split by 365. And now we're going to try and look at the formula. I'll set them up. So I've ran that calculation a number of times. Um, Nice to use your exponents button on your calculator. By the time you get to daily interest, make sure you're using as many decimal places as possible. Over the short term, the difference in interest rate doesn't appear to be that dramatic, but imagine having 18 years of this kind of interest and getting paid interest on your interest is a fantastic advantage. Let's try a couple of problems. So I like to translate the information from the problem. My principal is $7,000, and I'm going to deal with quarterly interest, which means my interest gets divided by 4. Convert that to a decimal. So 5 divided by 4, and then divide by 100, 0.0125. 1 plus 0.0125, and then I'm going to let that go for 6 years. There are 24 quarters in 6 years, and this should generate the answer. So hopefully this is a familiar problem-solving method. We've got a couple more to solve, so let's turn the page over. It's interesting to solve for something other than the amount. So in example 4, we're looking for the annual rate of interest. And in example 5, we're looking for how long it would take. So 2 different types of calculations. I'm going to set up what I know, and then we'll look at plugging into the formula. So I have my information identified. Now I'm going to plug it into the formula and see how I can use the new skills of the previous unit to solve for the unknown I or the unknown N. You should envision that we're dealing with something where logs can be helpful. So plugging in. So in both cases, I'm thinking that my first step is going to be division and then applying some log skills. Let's do the bottom one first. I'm going to divide by 8,000. So 16,000 divided by 8,000 is 2. So 2 is equal to 1 plus 0.005, which I can actually add. 1.005 to the n. And now with my unknown in the log position, I'm actually going to use log rules to help me solve. And I'm going to say that log of what is equal to n. I'm not sure which side you prefer. The green side takes my exponential form and converts it into log form directly. I can't plug that easily into my calculator, but I can convert the logs into a base 10 by going log of the argument divide by log of the base. I could also have taken 10 of the argument right away. So take log base 10 of 2, take log base 10 of the right-hand side of the equation, move the n down, and I end up with the same answer. I've translated my n to the closest whole number and translated that into years. That's 11 years and 7 months. In a similar fashion, I'm going to divide and then try to apply logs to that top one. Now, is this something I want to solve with logs or something I want to solve with exponents? I'm taking another look, and since my unknown is in the base, I think I'm going to solve with exponents. I'm going to raise both sides of the equation to the exponent 1/8, which is going to allow me to have 1 plus I on the right-hand side. And on the left-hand side, I've got to take the result of my division and raise it to the exponent of 1/8. So I've solved for my I, but remember that's my I for my semi-annual period. And I was having interest paid to me twice a year. So my annual rate of interest will be this number multiplied by 2, which is 7.4%, my annual rate of interest. So thank you very much for looking at money again. Hopefully the exercise goes quickly. We'll take a look at one more. I'll set up one more tonight. Thank you.